So, hello, my name is Jonathan Whitmore. So, who am I? My background is I did a PhD in astrophysics in 2011 from University of California, San Diego. I went on to do a postdoc in Australia in astrophysics. In 2014, I did an Insight Data Science Fellowship in 2014. And after that, I started working as a data scientist in Silicon Valley Data Science. I also did an O'Reilly screencast course called Jupyter Notebook for Data Science Teams, which is that little icon there in the lower right. So this is my background. I'll be talking to you about mental models to be using in data science. So here's a quote from Feynman, which I think everyone who's a scientist or data scientist can resonate with very well. The first principle of science, or trying to discover knowledge about the world, is that you must not fool yourself. And you yourself are the easiest person to fool. I think that's very appropriate and very true. So I'm going to start off with a few, I call them mental models for lack of a more concrete term. It's more of an umbrella term for strategies that people use and that they should be avoiding, and also making sure to try to incorporate into their own practice. So some things to avoid. P-hacking. So P-hacking, everyone knows P-hacking. If you don't know P-hacking, I'll explain it in just 1 second. But P-hacking, fishing expeditions, and researchers' degrees of freedom, these are all tied to the same kind of phenomenon. It's best explained by a comic from XKCD. So the comic begins, jelly beans cause acne, and they're asking for scientists to investigate this hypothesis. And they come back and they say, we found no link between jelly beans and acne with a p-value of less than 0.05. And they think that settles it, but then someone says, no, actually I think it's a certain color of jelly beans that causes acne, not just jelly beans in general. So they go off and they start testing individual color for jelly beans. So they say we find no link between the purple jelly beans and acne, no link between brown jelly beans and acne, no link between pink, so on and so forth. And they end up doing 20 different comparisons, and lo and behold, this one in the upper right, second to the right panel says, we found a link between green jelly beans and acne. So they did 20 different tests, and the news, of course, reports green jelly beans are linked to acne with a 95% confidence, only a 5% chance of coincidence. All right, so that's p-hacking. Everyone loves to point at that and say, clearly that's wrong, we shouldn't be doing that. And I think people who are aware of this might be lulled into a false sense of security about their own analysis. So let's look at one that's slightly more subtle than this egregious case. And it's one that's found in the wild. So here is a paper that it's called Gender Bias in Open Source, a pull request of acceptance of women versus men. And it's in this PeerJ link. I'd like to make a couple of caveats before I begin. First of all, this was submitted for comments, so I'm actually going to be commenting on the one that's submitted for comments, and there's multiple versions of this after this. So this is intended to be thought of as first draft feedback. And so I'm using just this first draft for didactic reasons, and it's currently not peer-reviewed. So with those two caveats out of the way, their analytical setup was actually really interesting. They're examining GitHub commits. They had over 4 million GitHub profiles with users and email addresses. They identified the gender of over 1.4 million of these users. They also had access to 2.3 million merged pull requests. Now, if you're not familiar with what pull requests are, they're basically you suggest code improvements or additions to some project, and if it's accepted, then it's a merged into the project pull request. And the research question is relatively well defined. Is there a gender bias in pull request acceptance rates? So the first question that they addressed in the paper is, are women's pull requests less likely to be accepted? Their hypothesis is, yes, it's probably that they're less likely to be accepted. And when they did the statistical test on this, their results showed that actually no, to a very small p-value, it looks like women's merge requests are actually higher significantly than men. And so they thought this was strange, so they had a second question, maybe. Sorry, did you see that? Yeah, okay. What if we exclude insiders from our analysis? So insiders are these explicitly authorized owners and collaborators of a specific open source project, and outsiders are other GitHub users. And they found that it continues to be a significantly higher acceptance rate than men. And so they go on and ask, well, maybe pull request acceptance rates start low and then they end up very high, and the people who keep committing are the high acceptance rates, so that's what's skewing the overall balance. And so along the y-axis here, you see the acceptance rate of the different genders. The top one is women versus men on the lower one. The x-axis is pull requests that have been offered. And it's on a logarithmic scale. For the first one is all the way on the left, and it goes the first, the second, the fourth, the eighth, the 16th, and so on, all the way along the x-axis. So you can see that even from the very first commit, the first commit that a woman gives versus the first commit that a man gives, it tends to have a higher acceptance rate. And so they go through actually many, many more of these. So I'll just briefly show you the conclusions part. So the observations that the paper that is reporting says women are more likely to have pull requests accepted than men. They continue to have high acceptance rates as they gain experience. They are less likely to serve an immediate project need. This was done in some cool way. Women's changes tend to be larger. Women's acceptance rates are higher across the top 10 programming languages that work on GitHub. And then they found, the sixth one is that women have lower acceptance rates as outsiders when they're identifiable as women. So that was the sixth and final observation on this draft one of this paper. So the plot for that one comes from here. So the left plot is insiders and outsiders, insiders, and whether their GitHub username or picture was gender neutral, and whether it was gendered. This is the first split. And on the right, it is outsiders who have gender neutral versus gendered GitHub emojis, avatars. And the actual difference between the men and the women in the gendered outsiders isn't statistically significant. But if you compare the women to the gender neutral in the outsiders, that is significant. So if you think back to the p-hacking scenario, where if you keep making many, many comparisons, multiple comparisons, eventually you will find something that you'll find a value that's significant, first of all, or if you have a hypothesis in mind, you can also end on that kind of a thing as well. There's actually an interesting sub-story in this as well. So it says it was submitted for commentary. A question was asked, do you have data on the gender of the users that are accepting the pull requests? And the author replied to this, or one of the authors. So our analysis, which wasn't included in this paper, that was for that, which we've cut out a lot, shows that women are harder on other women than they are on men, and men are harder on other men than they are on women, which is kind of an interesting sub-story to have. One of the things I would also like to point out is that they've cut out a lot of analysis. So they've actually done many, many more comparisons than they already showed in the paper. So they're doing this multiple comparisons problem is definitely a concern that should be raised. There are some statistical ways of dealing with this with like a Bonferroni correction or something else. But even then, I'll get to why that might not be enough in just a little bit. Of course, in just the same way that the p-hacking XKCD scenario showed how the media overreacts to this, or reacts in an interesting way, the media was less nuanced than the paper itself when Business Insider was like, sexism is rampant among programmers in GitHub, and they linked directly to this study. So media has their own agendas, of course. So it's interesting. So you can see how you could consider the second one more of a fishing expedition, where you just keep pulling back comparisons out until you find a comparison that is what you're either looking for, or something that's compelling, or something you think is publishable, right? Okay, so there's another flavor of this same category that I think is important to bring up. So it's easy at this point for people who are scientists to think, okay, well, I've not done the p-value one. That was clearly, obviously wrong, and probably not doing anything like the second one either, so I think I'm probably on solid ground. There's this very, very good paper by Andrew Gelman, and I'm going to pronounce his name, called The Garden of Forking Paths. And the title of the paper is actually the conclusion as well. So I'll go through the title slowly. The Garden of Forking Paths. Why multiple comparisons, the thing we were just talking about, can be a problem, even when there is no fishing expedition or p-hacking, and the research hypothesis was posited ahead of time. So saying there's still a problem of multiple comparisons, even if you have all these other things taken care of. So here's a hypothetical example that they gave. So imagine you would like to test the difference between Democrats and Republicans, And you're going to do this test by giving a math test in 2 different contexts, healthcare and military. And the hypothesis being that context matters, and one would expect Democrats to do better in the healthcare context and Republicans to do better in the military context. So this is just a hypothetical example. So already, you can ask the question, how many options for results are there? So the number of patterns that could be found among men, but not among women. There is a difference between the Republicans and Democrats and this math test, which could be explicable under the theory that men are more ideologically driven than women. Or it could be found among women, but not among men. So this is explicable under the theory that women are more sensitive to context. Or there could be a difference, it could be between the sexes in the healthcare context, but not within the military context. And so on and so forth. So there's many possible comparisons, even if you already have the research question stated ahead of time. So the conclusion that they have, researcher degrees of freedom can lead to a multiple comparisons problem, even in settings where researchers perform only a single analysis on their data. The problem is a fundamental one, and it comes from that there is a large number of potential comparisons when the details of data analysis are highly contingent on the data, without the researcher having to perform any conscious procedure of fishing or examining multiple p-values. Okay? So going on to another topic, just so storytelling. This is rampant in research as well as in business, where the basic idea is you explain the data with a plausible sounding story after you know what the answer is. So once you know the answer, then you say, oh, okay, that makes sense because, and then you go on with your explanation. So this is also known as harking from this paper in 1998. So it's hypothesizing after the results are known. So this is a hard one to avoid, especially if you're interacting with, say, managers or someone who is not trained in, even people who are trained, but especially if they're not trained in science or statistics, that they like to come up with stories after the fact, and it helps to essentially try to force them, before you tell the answer, make a hypothesis. If I told you the answer was X, what would that tell you? If I told you it was not X, what would that tell you? And forcing them to solidify their thoughts on this matter before they know the results is one way you can help avoid this just so storytelling problem. Any questions so far before I go on to the next section? Cool. All right, so I did a lot of examples on what not to use. Yes?
So there is another discussion that was going on in my company. That's called the Simpsons paradox.
Yes.
It sounds exactly opposite to what you're saying. Like, don't look at the confounding variables that might be possible.
Yeah, so Simpson's paradox is one where there's an overall trend that can even reverse sign if you actually take into account the various subcategories. So I have, one of the things I'm going to say in this to use will hopefully start to address that. If it hasn't, ask me again at the end and I'll come back. Sure, okay, the question was, this sounds in some ways the opposite of Simpson's paradox. Is that right? Okay. And, okay. So I said a lot of things to avoid, things to be wary of, things to be concerned about. So here are some things I recommend you using. So there's a strategy called consider the opposite. So this comes from a number of papers, but the one I'm citing here is called, the source of it is Consider the Opposite, a Corrective Strategy for Social Judgment, where they actually tested whether, they asked people to make a judgment on a specific thing, like the height of someone or whatever, and they gave them 2 different ways. Say, like, please be as unbiased as possible, be as fair as possible, and go. And then the other group of people, they said, consider the opposite of the hypothesis you currently have. So if you think that they're, let's say, shorter than someone else, consider maybe they're actually taller. And as long as it's kept to a reasonable number of alternative hypotheses, so like a couple rather than like 50, this apparently has a better corrective strategy than just emphasizing people, please be unbiased, please be fair. So considering the opposite just helps you get closer to the correct answer than the reverse. Asking yourself this question, which I alluded to a little bit earlier, what would change your mind? Specifically, let's say you have a belief A about the world. So frame it as a hypothesis. A is how the world works. So ask yourself and encourage others to ask you, what would it look like if your hypothesis were wrong for a hypothetical case? This is a way of getting at falsifiability, but you say, okay, let's assume it's wrong. And what do I mean by that? So let's just go through a specific example. So let's say your hypothesis was that every action anybody ever takes, ever, is done for selfish reasons. So do a thought experiment and challenge it in this way. So say for the sake of argument, Alice actually did an unselfish act. So we're in this hypothetical realm where we had a person who actually did something that was unselfish. How would you recognize that this just happened and that your hypothesis is incorrect in this case? If the answer is nothing, if there is nothing that you could do to figure out that your hypothesis got this wrong, then your hypothesis is unfalsifiable in principle, which is different than unfalsifiable in practice. But the basic problem with that is that your explanation has zero explanatory power. Even getting it wrong looks like you got it right. So if you can't do this kind of thing, this is one easy litmus test to say, okay, I need to think about a little bit more carefully about how I could, what would change my mind, some sort of evidence that would look like X, Y, or Z. Okay? So I'd like to go into another study that was done on the rates of red cards being given to players. So this paper, it comes from this paper here, which is called Many Analysts, One Data Set, Making Transparent How Variations in Analytical Choices Affect Results. So they crowdsourced their analysis. They put out a call for a proposal for analysts to do some analysis on some data that they had. They gave every team of analysts the same data. They gave them the same exact research question. So are soccer referees more likely to give red cards to dark skin-toned players than light skin-toned players? So they have a specific research question, the same data set, and they had 29 research teams composed of 61 total analysts. Going back to the multiple comparisons problems and analytic choices that are being made. So everyone has to use, because you're trying to say what is the effect of skin tone on getting red cards, you have to choose covariates in the data, some other variable that you're also going to consider in this analysis. So here is a plot of the different covariates that were available. So along the x-axis, you see the player's position, their height, their weight, their age, which league, country they're in, and so on. Many different choices here. And along the x-axis, if there's a black square there, that team number along the top used that covariate. So the covariate that was most commonly used was position, and only 62% of the teams chose it. And then from there on out, you can see this. So people made many, many different choices on which covariates to use. And this was actually done in a really cool way. They did a round-robin style thing. So they first gave everyone the data, the research question. They did analysis, wrote up the analysis, got an answer, and submitted all of their results back to the central author, who then took away the results and collated everyone's research that they had done so far and put it back out to all the remaining teams for feedback. So they got a second round of eternal peer review, basically, saying, here's what I think you should do better, here's what not, and everyone gave reasons for why they're including or not including these covariates, and they're all very reasonable sounding. Like, oh, I shouldn't use position because of X, Y, or Z, and whatnot. And still, here are the different analytic approaches that were used. This is just a zoom in of a few of them. So one analytic approach was zero-inflated Poisson regression. Another one was Bayesian logistic regression. We have hierarchical log linear modeling, multi-level regression. So many different ways of attacking this problem. And the results, here's a 538, the political blog's visualization of this paper result. Shows, so equally likely is that the thick black line along the bottom here, if I I won't use my mouse, but along the bottom there's a equally likely between light skin and dark skin toned players to get a red card, and whether it's significant or not. And the odds ratio going, it's more likely that a dark skin player is to get a red card is farther up. And the error bar sizes change drastically. The results change between significant and not significant. The basic conclusions are this. So no teams found a negative effect, that it went the opposite way than expected. 9 teams found no significant relationship whatsoever, and 20 teams found a positive effect. So they said, and this is from their paper directly, selecting randomly from the present teams, there would have been a 69% probability of reporting a positive result and a 31% probability of reporting a null effect. This raises the possibility that many research projects contain hidden uncertainty due to the wide range of analytic choices available to the researchers. So this hopefully doesn't make you disheartened about what can science teach us about anything. But it is something to be aware of. So this was done as carefully as possible. This was definitely not a multiple comparisons problem. The people were choosing it in different contexts entirely and getting peer review before they even released it. And still they had results ranging across this entire effect size. So it should be at least somewhat sobering. So one way to help address this problem is something called blinding analysis. Now you might have heard of double blinding. So double blind studies are the gold standard in clinical trials and whatnot. So it's where the experimenter and the subject, neither one knows who's getting a placebo, who's getting the actual drug, and so on. And that's not what I'm talking about when I say blinding analysis. So blinding analysis is essentially a principle more than it is a technique. And the principle is, do not let the expectation of a particular result drive model revision. This comes from, it was, I guess, popularized in particle physics, where they have a long history of this, of being self-critical of what they're doing. So a blind analysis is a measurement performed without looking at the answer and is the optimal way to avoid experimenter's bias. So to give you a sense of what this looks like from a physics perspective, these are 4 different physical measurement values. The actual measurements of them aren't particularly important, but this is published date versus the findings for these different values. And you can see that there's trends over time of what the value is for these different constants. Some of them start high and end up going low, and so on and so forth. And so they started, after realizing that people are doing things like, hey, this looks like it's a 3 sigma effect compared to what was published last year. Maybe we got something wrong, and then they'll go back and double check it. And so they'll double check it when they realize that it doesn't match the previous one, and maybe you look and you find something in your analysis that, oh, of course, I did this wrong, huh, and you fix it, and it gets back to the right answer. You can start having these problems. So to keep yourself from doing this, they did a blinding analysis. And, excuse me, there's a Nature blog post about blinding analysis, which has this nice quote. Excuse me. Because many analytical decisions and computer programming bugs can't be anticipated, investigators are forced to make decisions knowing, either consciously or unconsciously, how their choices will affect the measured result. So you're trying to measure the lifetime of a particular meson or something, and you know the answer. It can lead to either conscious or unconscious changes in that value. Blinding analysis enables the investigator to engage in the analysis and exploration and finalization without worrying about such bias. Since you don't see the answer, you can't be biased toward what you think the right answer is. So to give you a concrete example of what this means, I'll give you a quick interactive example. So this also comes from that same Nature blog post of blind analysis to hide results to seek the truth. There's different techniques, blinding techniques. You can add noise to the data. You can actually bias the sample in some way. You can scramble things. I won't go into this, the details of the actual techniques for it, except to show you one. So here's just a simple Python object called blinders. And what it's going to do is blind the result from stats models so that when I'm doing this analysis, I can't know the answer. So let's say I wanted to do my own, so I saw the red card study from before, and I thought this was fantastic. I wonder what I would get for the same analysis. I get the data and I start working on it. I already know that, say, 20 of the results were at like odds ratio of 1.3, so I kind of have an idea of what the right answer is, right? So if I simply, and I mean blinding in this way, like so say the red card propensity as a function of skin tone, height, and position. Let's say those are the covariates I start with, and I run some logistic regression or ordinary least squares. When I view the summary, using the model.summary from stats models, it shows you every coefficient. But in this case, if I say I want to blind myself to the effect of skin tone on this analysis, the analysis is still run. Everything happens. The only thing this blinding thing does is print nans for this row. So everything about the analysis is still done. It's still in that model object. I've not changed the values of anything. This is just a blinding for my effect. So now that if I decide, do I want to continue to keep, should I add position? Should I add weight perhaps, or height? I know that if I'm adding that to the model, or making these choices, I'm not making it based on what I know the variable to have an answer for. Okay, so this particular implementation, I'll give you a link to it at the end of the talk. It's not that important. What's more important is the principle itself. All right, so with that, I'll go on to my conclusions. So conclusion one, first of all, realize that science and data science, statistics and whatnot, is actually harder than you probably think it is. It's a really hard thing to do correctly, and acknowledge that. Beware of this garden of forking paths problem, where you have multiple comparisons that can be possible even if you run only a single analysis on your result. Try to avoid just so stories. Consider the opposite. Be explicit and try to be precise in what it would take to change your mind from a particular belief or strategy that you're currently taking. When possible, try to blind your analysis in whatever way you can, so that you're not unconsciously or even consciously trying to get to the right answer. And a thing that I didn't talk about is this thing called threshold out, which is a reusable holdout set. And I've provided some links to this in this final thing here. So thank you very much. This is my contact information. So Jonathan, that's my email address, Twitter, and the sources I put in this talk, I will also put up the slides as well, are all available at this bit.ly link. So if you go to this bit.ly link, you'll have sources to the blinders code that I put in there, and all these other things. So that's a one-stop shop for your resources. If you saw something in the talk that's not in there, send me a message on Twitter, send me an email, and I'll add it to that list. Thank you very much.
Hi, great talk. Thanks very much. My question goes back to the analysis of GitLab merge requests. GitHub. And I was just wondering, what was the effect size for the one gender difference they found? It seems to me like my experience that often closely tied to p-hacking is just reporting on results that are just not very big.
Yeah, sir, I'll use the microphones instead of yelling. Okay, so the y-axis goes from 60%, this is 70%, so the first two tick marks between 60 and 70. So the effect size between these two, this looks like about 62.5% for women, and it's probably 63.5 for men, so about a 1% difference in effect size.
Right, so I'm wondering, do you think that's another filter we should apply to analysis?
That the effect size has to be large? I don't know. I think that might be too restrictive of a requirement.
Even if it is a robust finding, that's 1% difference, is it really?
Yeah, okay, so I will say definitely that you should strongly consider the effect size as whether it's important or not, definitely. So you can have a statistical significance without it being significant in practice, essentially. And that is an important thing to keep in mind. I don't know that I'd use this as a red flag to say that maybe you're doing p-hacking or something, though. I'll repeat your question. So.
So speaking of kind of like well, a lot of things you're talking about, there's an idea that you have this 10% holdout validation set that you never touch until the end of your analysis.
Yes.
How does in some sense it kind of does what your blinding is also supposed to do. So what's the difference between having data you never look at and then applying a model to
So I would just like to point out, with a holdout set, sometimes it depends on the case, because holdout sets could be done for, like, say, an internal company reason. So, like, you have a holdout set that you run models and do hyperparameter fits on it to decide it. So you're actually running against the same holdout set many, many times. And that kind of a thing, you're doing an overfitting, even though it's a holdout set, right? So that's why I'd like to actually highlight this just real quick. This work by Cynthia Dwork and a lot of other people. It's called the reusable holdout, thresh holdout. And it is a way of being able to, in a statistically valid way, repeatedly look at a holdout sample, which is what people basically do anyway. So this is also included in that resources thing at the end. But one of the quotes that they have from that paper is that modern data analysis is inherently adaptive. So you actually look at the answer many, many times. One way to help yourself not get driven the wrong way is blinding. Another way is to use a holdout set. And if you're going to look at a holdout set many times, then you've thrown away the reason for doing a holdout set. So thresh holdout is a very, very cool idea that I think should get more attention.
Can I follow up on this? Do you
Yeah.
foresee like data analysis taking a more like engineering approach to where there are set like protocols for doing certain kinds of analysis? Because it is a lot of data analysis is very inherently an adaptive process, whereas in other disciplines there's like these engineered ways that you go down this path and do the analysis exactly this way.
Yeah, so the question is there a preset, like a canned way of doing an analysis that you can just say, this is definitely the right way to do it for some, say, new data coming in? Have I seen that kind of thing? You could do that. I think that comes into starting to be almost report generation. Like you say, okay, well, what is this month's analysis? Once you have everything tweaked and stuff. I think once that is done, it comes out of science or data science and into something, as you said, like engineering or report generation, which is very useful as well, but it's just a different thing. Any other questions?
Curious sort of how you learned this sort of stuff. So like my background is statistics economics, which I think has a lot of training of like economists sit in rooms and will do consider the opposite thing to try and make each other look stupid.
Yeah.
So you sort of have those lessons burned into your brain from that. But I don't think a lot of like sort of data science training is, you know, more how can you predict things really quickly versus how can you causality. So coming from a sort of physics background, how did you get this?
Yeah, so the question is how do people in general learn this stuff in the best way possible? I don't have, besides reading widely and trying to just figure out what's going on and try to figure out what the best practices should be, I don't have much advice. I mean, so in astrophysics, we also have a similar kind of thing where you just like, you present your results and everyone's like, did you consider this? Have you thought about that? Maybe you should try your analysis by doing X, Y, Z, right? So we have a similar kind of crucible of fun, let's call it, when you give a talk, and there's constructive criticism going on to shore up your analytic chops. But outside of that, just read as much as you can. Sorry, I don't have a better answer. Yeah.
For you, this sort of thing, like common questions on findings, I mean, it seems like it would be hard to find things about, like, if you were looking for bias in like, intersectionality, because, like, that's inherently, like, you know, breaking into, like, you know, the ports.
Yeah.
I mean, how would you go about, like, investigating something like that?
So how would you, okay, so the question is how would you work on doing analysis where there is multiple splits on the data set and so on and so forth? Well, one way you can do this is to actually put these in a regression that allows for either like Simpson's paradox kind of thing to be teased out for this, so that you're having an overall effect plus an effect on the various things you're concerned about holding constant or doing. So that's at least one approach for that kind of thing. More specific than that, I don't have advice, but.
But you think, like, having, like, one set thing you're looking at the beginning and not then later teasing out more, like,
So anytime you're using the data itself to drive your analytic decisions, you're in trouble. You're in like danger zone. You're not necessarily definitely doing something wrong. It's just like there's a blinking red light over your head, and it should be blinking louder as you keep going. So I think doing like regression, multiple, like that helps, as well as blinding the analysis. I think with blinding, you at least know that you're not going toward a result that you have a preconceived notion for, that you're trying to find. If I get this, I get a publication. If I get a null result, nothing, right? So I think that can help. And good luck. It's hard. We're done? Okay.
Thank you very much. Jonathan Whitmore, data scientist at Silicon Valley Data Science.